Welcome back, everyone. In this unit, we are going to be talking about the greenhouse effect. So our goals for this lesson are pretty straightforward. First, for you to be able to explain the factors that make up the Earth's energy balance. And then second, understand how greenhouse gases warm the Earth. So let's start with the idea of the energy balance of the Earth. So we're looking here at energy coming in and energy going out. So any object that's hotter than absolute zero, so you remember absolute zero, that's the lowest possible temperature where all of the atoms in the object are completely stationary, there's no movement to them at all. So anything hotter than absolute zero, which is essentially everything that we've got, is going to radiate energy. So some of that thermal energy is going to turn into electromagnetic radiation coming off of the object. The hotter that object is, the more energy it will emit, so there'll be a larger amount of electromagnetic radiation coming off that object, and the shorter the wavelength of that energy. So you recall our electromagnetic spectrum, we have a range of different types of radiation depending on the wavelength, right? The distance between two peaks as it goes up and down. So a hotter object will both emit more energy and will emit energy at shorter wavelengths. And so you can see in the diagram there a comparison between the sun and the Earth. And you see the sun one is scaled way down just to fit it on the diagram there, right? It should be far, far, far taller than the Earth one, even more so than it is on the diagram there. So that should make sense. The sun is a lot hotter than the Earth, right? The sun is nearly 6,000 degrees. So it is blasting out enormous amounts of energy from that. The Earth is producing less energy because we're not as hot as the sun, but we're still producing some energy because we're warmer than absolute zero. So the sun is producing more energy, and you'll see that the sun's energy is mostly at shorter wavelengths. So the sun is putting out short wavelength energy, which happens to fall in the visible light portion of the electromagnetic spectrum. Right? That's why we see the sun lit up because the peak of its energy production is in the wavelengths that constitute visible light. The Earth is producing radiation that is longer wavelength, so we can't see it. We don't see the Earth glowing. Most of the Earth's energy is coming out in the infrared part of the spectrum. So we've got the sun putting out visible light primarily, the Earth putting out infrared radiation. But in both cases, because there are objects warmer than absolute zero, they're putting out some radiation. So of course, a portion of that radiation put out by the sun hits the Earth. And that radiation from the sun that hits the Earth, we call insolation. So that's just an abbreviation for incoming solar radiation. So incoming solar radiation, or insolation, is the energy that comes from the sun to the Earth. So that portion of that mostly short wavelength visible light energy that we are receiving. And the way that we're receiving that insolation shapes our seasons. So the axis of the Earth is tilted about 23.5 degrees away from being perpendicular to the plane in which we orbit the sun. So as the Earth is going around the sun, if you imagine that circle as kind of a flat plane there that circle is drawn on, right? We treat that as horizontal. Then the Earth's axis is not vertical, it's tilted over about 23.5 degrees. And it's tilted so that it's always pointing in the same direction in the larger cosmos. So right now, the northern end of that axis, so if you were to create a line, following the Earth's axis out the North Pole and just keep going for many, many light years, you would eventually wind up somewhere in the neighborhood of the star Polaris, which we call the North Star. That is something that changes over the course of millions of years as stars move in our galaxy, etc. But at the present moment, our Earth's axis at its northern end is kind of pointed towards Polaris, and it stays pointed there regardless of which side of the sun we are on. So that means that for one portion of the year, when the Earth is kind of in between the sun and Polaris, then the northern hemisphere is pointed away from the sun. It's tilted away from the sun 23.5 degrees. And then we get to the other side of the Earth's orbit. And so now the Earth is on the opposite side of the sun from where Polaris is. And so the northern hemisphere is tilted 23.5 degrees towards the sun. All right, so for part of the year, the northern hemisphere is tilted towards the sun. For the other part of the year, it's tilted away from the sun. And then the southern hemisphere will have the opposite. So when the northern hemisphere is tilted away, southern hemisphere is tilted towards the sun. And so that's why seasons are the opposite in the northern and southern hemispheres. So as I'm recording this, we are getting into the fall season here in the northern hemisphere, moving towards winter. But at the same point in time in the southern hemisphere, in say Australia, they are in the spring, moving towards their summer, because the Earth is approaching the point where the northern hemisphere is tilted the most away from the sun, southern hemisphere tilted most towards the sun. So when a hemisphere is tilted towards the sun, it's going to receive more insolation. It's going to get more radiation from the sun, and that's for two primary reasons. One is that the solar radiation that's hitting the Earth is more direct. So if you recall our discussion from our last lesson about why we get more energy hitting the equator than the poles, right? At the equator, the sun is more directly overhead, coming in at a steeper angle, and so that concentrates the sun's energy on smaller areas of territory. So any square meter of surface is getting more energy when it's coming straight down than when it's coming in at a shallow angle and spreading out. So when your hemisphere is tilted towards the sun is farther overhead, right? The sun rises higher in the sky during the summer than it does in the winter, so we get radiation that's coming down closer to directly overhead. Here at Slippery Rock, we're far enough north that we never get the sun directly overhead, but it's still higher in the sky and closer to vertical during the summer. So we're getting that more direct insolation. It's more concentrated energy, and we also have longer days. So the sun is lighting up the half of the Earth that's facing toward it, which means that if you're tilted towards the sun, your hemisphere is tilted towards the sun, you're going to stay in that lighted half for a longer portion of the day. So your day length is going to be longer than 12 hours while your hemisphere is pointed towards the sun, and your day length is going to be shorter than 12 hours when your hemisphere is pointed away from the sun. So you're receiving more direct insolation during the summer, and you're receiving it for a longer portion of each 24 hours because the sun is in the sky for longer. So between those two factors, longer days and more direct insolation, we get warmer conditions, more energy, more warmth during the summer when your hemisphere is tilted towards the sun, colder, less energy when you're tilted away from the sun. This is not an effect of the distance that we are from the sun, because in fact, the northern hemisphere summer occurs when the Earth is generally farther from the sun than during our winter. We are actually closer to the sun during the winter than we are during the summer, because the tilt of the Earth's axis is what really causes the seasonal difference. It's not the distance to the sun, because the variation in distance that we get from our farthest to our closest point is only a few percent. So it's not making a huge difference in the amount of energy that we're receiving. Okay, so let's look at what happens as that insolation comes to the Earth. So we're getting all of this energy beamed from the sun down to the Earth. It is mostly in this short wavelength, mostly visible light portion of the spectrum, and it hits the surface of the Earth. And so some of that energy is going to be reflected off the Earth back into space. So it's just going to bounce off the Earth, and it's going to go back out into space in the same form that it came in. So when that energy is reflected, it doesn't change anything about its form, it just changes direction that it's going. So the reflected energy is going to still be that shortwave, visible light, mostly energy. But then some of it is going to be absorbed by the Earth. So the Earth is going to absorb some of the energy that is coming in from the sun. That is going to warm up the Earth. And then because the Earth is warm, it is now going to create its own radiation going out. Right? So the Earth's going to absorb some of that energy, warm up, and radiate energy back out into space. And because the Earth is not getting nearly as warm as the sun is, it's going to radiate out that energy at a longer wavelength, so mostly in the infrared part of the spectrum. So in the simplest terms, we can look at that insolation coming to the Earth. Some of it's reflected off into space still as short wavelength visible light. Some of it's absorbed by the Earth and then re-radiated back out as longer wavelength, mostly infrared radiation. So one thing we might want to know is, what's the ratio between those, right? How much of that insolation is just getting reflected back into space without being absorbed by the Earth? And we can describe this as the Earth's albedo. So the albedo is, in technical terms, the percentage of insolation that's reflected by the surface of the Earth, the percentage of that incoming radiation that just bounces back off into space. Another way to think of that is this is kind of the shininess of the Earth. Right? When an object is shiny, light is bouncing back off of it, whereas an object that's not shiny is absorbing more of that light. So the Earth's albedo varies dramatically depending on what is on the surface of the Earth. Different kinds of land cover, different kinds of surfaces to the Earth are going to have very different albedos. And those albedos more or less track the color of the surface. So light-colored surfaces have a high albedo. They reflect a high proportion of that sunlight back out into space. Dark-colored surfaces reflect a low proportion of that sunlight, so they have a low albedo. They're absorbing most of the sun's energy. So if you look at this diagram here, and it's showing you kind of the typical range of albedos for different kinds of things on the Earth, you notice the things with the highest albedos are things like fresh snow and various kinds of clouds, right? Those are all things that we know are white. So very light colors, they're reflecting a large portion of the sun's energy back. And you've probably noticed this if you've ever gone outside when you have a lot of freshly fallen snow, but the clouds have cleared up, so you're getting a lot of sunlight coming down, and you get kind of blinded by all of the sunlight reflecting off of that snow. So that snow is going to have a very high albedo. It's reflecting, sometimes more than 80% of the sunlight that hits it right back into your eyes. So it's like 80% of how bright it would be to just stare directly at the sun. And so light-colored things, high albedo, reflecting a lot of visible light back off the surface. Then you can see we get to some darker things. So you can see like desert land cover. It's going to have a somewhat lower albedo than plant cover, right? Like a forest is going to have an even lower albedo. Water or dark, wet soil are going to have some of the lowest albedos of natural land covers. So depending on what surfaces are on the Earth, that's going to shape how much of that sun's energy is bouncing off the Earth back into space. And one thing to note here, the chart there is showing generally natural land covers. We have crops on there, which would be planted by people, but most of these are natural land covers on the chart. But we also can think about other human-made surfaces. So the things that we typically would find in an urban environment, so things like asphalt on roads and parking lots and shingles on houses, those tend to be, kind of in very broad average terms, they tend to be lower albedo, so they're absorbing more energy, reflecting less energy, tend to be lower albedo than a lot of natural land covers, particularly the natural land cover that might have been in that place before the urban the urban environment was created, right? So if you compare a forest that might have grown in an area to the city that was built when the forest was cut down, that city probably has a lower albedo than the forest. So urban landscapes are absorbing more of the sun's energy. They're reflecting less of it, so they're absorbing more of it. And this creates what's called the urban heat island effect. So because urban landscapes tend to absorb more of the sun's energy, that's going to heat them up more than a nearby non-urban, like a natural or rural kind of landscape. So you'll often find that it's noticeably warmer in a city than it is in the nearby rural areas because that difference in albedo. And there are actually efforts these days to try to counteract that by deliberately creating higher albedo surfaces in urban areas by, for example, painting roofs white. So rather than dark colored shingles that absorb a lot of the sun's energy, you have a white roof that's going to reflect more of that away. And that might be a way to offset that urban heat island effect and keep cities cooler when it is really, really sunny out during the summer. Okay, so we talk about this in terms of Earth's energy budget because just like your money budget, this all needs to balance out. So in the long run, the amount of energy coming in needs to balance the amount of energy going out. And so if more energy comes in, an object like the Earth will warm up until the point when that warmer object is now emitting more electromagnetic radiation that then counterbalances the energy that it's receiving. And if it starts receiving less energy, then it will cool down and that will reduce what it's radiating out. And so over the long term, those things will balance out. But in the short term, they might get out of balance, right? 'Cause that's a process that takes some time to even out. So we can calculate this by looking at the incoming energy, insolation, and the albedo. What proportion of that incoming energy is reflected away, doesn't get absorbed by the Earth. And that will help us calculate the temperature that the Earth will end up becoming in order to balance out the incoming and outgoing radiation. And we call this the Stefan-Boltzmann law. So named after the physicists that discovered this relationship. And you can see the equation there. I'm not going to ask you to calculate things using that equation, but I put it there as an illustration that, there is an equation for all this, and you can see that equation is based on, take your insolation times 1 minus albedo. So the albedo is the percentage of insolation that's being reflected away from the surface. But for the Stefan-Boltzmann equation, we're interested in the percentage that's being absorbed, which is just 1 minus the percentage being reflected away. So you multiply those together, then you take the fourth root times 45.8, which is just one of these kind of physical constants, and that will tell you the temperature in Kelvin that you would expect the object to be and sort of settle in in the long run as it balances out the energy in and the energy out. So if we do that, if we take what we know about the Earth's average albedo, right? So we take all the different surfaces on the Earth and we kind of average them together based on how much land and ocean each of them take up on the Earth's surface, and we take our insolation that we're getting from the sun, we plug it all into the equation. What that tells us is that the Earth's average temperature is negative 18 degrees Celsius. So that's what the Earth's temperature should be based on the amount of insolation we get and the albedo of our surface. However, that is not the actual temperature of the Earth. So the Earth's actual average temperature is about 15 degrees Celsius. The Earth is much warmer than the Stefan-Boltzmann equation tells us it should be. And the reason for that is because the Earth has an atmosphere. So that negative 18 degrees Celsius is actually what the temperature of the outermost layer of the atmosphere is. So if you go to the outside of the atmosphere, that's the temperature that you'll find. It fits the Stefan-Boltzmann equation. But it's much warmer down here on the surface of the Earth because we've got the atmosphere wrapped around it. So we can revise our understanding of the Earth's energy budget to show that we've got short wavelength visible light coming in from the sun. It hits the Earth's surface. Some of it is reflected back off into space. The remainder is absorbed by the Earth. What's absorbed by the Earth is radiated back out, but that outward radiation has to pass through the atmosphere. And as it does, some of that energy is absorbed by the atmosphere. So it's not all getting through back out into space. Some of it's being absorbed by the atmosphere, and then it heats up the atmosphere, and the atmosphere now radiates in all directions. So the atmosphere will re-radiate some of that energy out onto space, but it will also radiate some of it back down to the surface. So the surface is now absorbing energy both directly coming in from the sun, but also it's absorbing some of that infrared radiation being re-radiated by the atmosphere. So we're getting additional energy coming back to the surface. So for the surface to be in balance, the surface ends up warming up even more than the outermost shell of the Earth is. So there's some of this energy that's essentially getting trapped in this system where it bounces back and forth between the atmosphere and the surface. And by having that extra energy circulating in here, bouncing back and forth between the atmosphere and the surface, that's going to raise the overall temperature of the surface of the Earth to that roughly 15 degrees Celsius that we were talking about. So why would the atmosphere do that? Why would the atmosphere absorb and re-radiate some of this energy? Well, it's because the atmosphere contains what we call greenhouse gases. So they get this name because the effect is kind of similar to what you'd get in a greenhouse. So a greenhouse is made out of glass, which ends up having a similar property to the greenhouse gases, where sunlight comes in through the glass, but then as the stuff inside the greenhouse that was warmed up by that sunlight re-radiates back out, some of that energy gets absorbed by the glass and radiated back into the greenhouse. So it keeps the greenhouse at a warmer temperature than the outside that isn't sheltered under this glass. So the same thing is being done by these gases in our atmosphere, so we call them greenhouse gases. So most of the gases in our atmosphere are transparent to radiation at both the short wavelengths that it comes in from the sun and the longer wavelengths that it gets radiated back out by the Earth. So it does not block either of those kinds of radiation. They will go right through it as if the atmosphere wasn't even there. So that's true of the biggest gases in our atmosphere. If you remember from our previous lesson, right, our atmosphere is mostly nitrogen, and nearly all of the remainder is oxygen. Then we got a little bit of argon as the third biggest one. All of those gases do not interact with this radiation. Let it come in from the sun, let it go back out, radiated from the Earth. But there are some gases in the atmosphere that are transparent to the shortwave radiation as it comes in from the sun. They let it pass right on through, but they will absorb and then re-radiate the longer wave radiation that the Earth is putting out. So they are sensitive to those longer wavelengths of radiation. So they will trap some of that radiation by absorbing it and then radiating it back out down to the surface. And so those gases include things like carbon dioxide, methane, nitrous oxide, and water vapor. So those are some of the most common gases in the atmosphere that have this property that they allow the short wavelength insolation to come right on through, hit the Earth's surface, and get absorbed, but then they will absorb and re-radiate the longer wavelength radiation that's coming off of the Earth. So they act as kind of that blanket or the greenhouse that is holding some of that energy on the Earth. So why would they do that, right? Why are some gases greenhouse gases and others are not? Well, it has to do with how the molecules are able to vibrate. So when these molecules are absorbing energy and then re-radiating it, it's based on the movements of the atoms within the molecules. So very simple molecules have very limited ways that they can vibrate. So something like argon is just a single atom. So argon doesn't form multi-atom molecules, it's just single atoms of argon. So all argon can do, it can move around, but it doesn't change its shape because it's just a single atom. Then you have something like oxygen, forms very simple molecules. So most of the oxygen in our atmosphere is O2. It's two oxygen atoms that are connected together by a chemical bond. And so that, in addition to moving around, the oxygen molecule can do one kind of vibration. The two oxygens can move apart and back together. So it can stretch and squish. That's the one motion that it can do within itself, the one way that the molecule itself can change shape. Same thing is true for nitrogen. Most of the nitrogen in our atmosphere is N2, same setup, two nitrogen atoms connected by a chemical bond, and so it can stretch and squish, but that's the only way that it has to change shape. So that means it's not going to be very sensitive to many types of radiation, because that vibration is what will cause that molecule to interact with electromagnetic radiation. So these simple molecules have limited ways they can vibrate, so they're going to have very limited interactions with electromagnetic radiation passing through them. But when we get more complex molecules, they have more ways that they can vibrate. So if we look at carbon dioxide, CO2, so that is basically, it's a carbon with an oxygen on either side of it. So now we can stretch and squish like the O2 does, but we can also kind of wobble. So you can imagine that carbon can move back and forth between the oxygens. So it can get close to one oxygen and farther from the other, and then the other way. Right? So the carbon can move back and forth between the oxygens in addition to the whole molecule stretching and squishing. That's more kinds of vibration, so there's going to be more wavelengths of electromagnetic energy that the CO2 can interact with, so it's going to be able to absorb some of those wavelengths and then start vibrating, and then its temperature increases and it will re-radiate out electromagnetic radiation. You get to something like water, that has even more complex kinds of vibrations that it can do. So water, H2O, it's an oxygen with a hydrogen on either side of it. So it can do all the things that CO2 can do, right? It can stretch and squish. The oxygen can move closer to one of the hydrogens and then farther away. But then another thing that water vapor can do is it can change its angle. So CO2 is kind of in a line. So the molecules are going to stay in a line all the time, but water is at an angle. The two hydrogens are not directly opposite each other on either sides of the oxygen, and so that angle can change. So a water molecule can vibrate by the two hydrogens swinging close together and swinging farther apart, so kind of straightening out and folding up. So it's got that additional form of movement that the molecule can do, and so it can interact with more wavelengths of electromagnetic radiation, and so it's going to be able to absorb those forms of radiation and then re-radiate them back out. So the more complex a molecule is, generally, the more wavelengths of electromagnetic radiation it can interact with, and so the more potential it has to act as a greenhouse gas. So we can see that on this chart here. So the upper portion of the chart is showing our radiation from the sun and from the Earth. And so on this one, they've scaled the sun all the way down to the same height as the Earth one, just so you can easily see them on the diagram. Remember that the energy coming from the sun is way bigger than what comes from the Earth. But the red line there, that shows our expected radiation from the sun based on its temperature. So that comes from looking at the Stefan-Boltzmann equation. We can see how much radiation we expect to get out of the sun. But then the colored in portion underneath that the line shows the energy that actually reaches the surface of the Earth. So we can see most of the energy that the sun is emitting is making it to the surface of the Earth, but you can see some little gaps, right? So, some little holes in there, some areas underneath the the red line that are not solid red. So there are a few wavelengths of solar energy that get absorbed even before they reach the Earth's surface. You see that even more dramatically when you look over at the blue portion showing the Earth. So again, the blue line, is the radiation the Earth is producing based on its temperature. So the Earth is radiating out all of this energy. Then the colored in portion is the energy that actually makes it through into outer space. So the energy that actually manages to leave the Earth. And so you can see with the Earth's radiation, there's a lot of radiation that the Earth is producing that never makes it out into space. And that's because the Earth's atmosphere is absorbing radiation at specific wavelengths. So the first bar there is the total absorption of radiation by all of the gases in our atmosphere. And you can see that if you look at the portion that's underneath the Earth's outgoing radiation, they're kind of mirror images of each other, right? All of the areas where the Earth is not emitting radiation that it's producing, that's because it's getting absorbed by gases in the atmosphere. And then the bottom part of that chart breaks it down by the specific gases. So you can see water vapor, that has the most different ways to vibrate of all of the molecules that we looked at. And so there's a whole bunch of wavelengths of outgoing radiation from the Earth that are getting absorbed by water vapor in the atmosphere. And so not getting back out into outer space. Then you can see carbon dioxide is grabbing some more of those wavelengths. We've got ozone. Right? Ozone is O3. It's 3 oxygens, so it has more ways to vibrate, and then it can act as a greenhouse gas. Methane, which is CH4, so 1 carbon, 4 hydrogens. Again, complex molecule, more ways to vibrate. So it's going to interact with certain wavelengths of outgoing radiation and trap them on the Earth. Nitrous oxide's got its wavelengths that it grabs. So when we add all those different gases together and the different wavelengths that they interact with and that they are going to absorb rather than letting it pass through into outer space, we get this greatly reduced amount of outgoing radiation from the Earth. We're trapping this energy on the Earth, and the Earth is warming up to compensate. So we can look at the change that's caused by this in a few different ways. So one of the ways that we might look at these different gases is in terms of what's called global warming potential. So global warming potential, how much warming is caused by a certain gas as compared to the same mass of CO2. So CO2, carbon dioxide, is our reference point, and we can look at other gases in terms of how many times more or what fraction of the warming caused by CO2 will be caused by an equivalent mass of this other gas. And we use CO2 as our baseline for a couple of reasons. One, it's the greenhouse gas that people are producing the most of, and because it happens to be the weakest of the greenhouse gases that humans are producing more of. So CO2 has global warming potential of 1. That's just, by definition, it's our reference point. And then you can see methane, for example, has 28 times the global warming potential of carbon dioxide. So 1 kilogram of methane will warm the Earth 28 times as much as 1 kilogram of carbon dioxide. And then you can see other things have even bigger global warming potentials. So nitrous oxide is 265 times as powerful as carbon dioxide. SF4 is 23,000 times as powerful as carbon dioxide. So carbon dioxide is pound for pound the weakest of our major anthropogenic, that is made by people, greenhouse gases. However, the reason we talk about CO2 all the time is because there's just a lot more CO2 that we're putting into the atmosphere, and a lot more CO2 that was in the atmosphere to begin with, right? The atmosphere is a major stock in our carbon cycle, so there's already a whole bunch of CO2 in the atmosphere, and then people are just putting out so much more CO2 than anything else. So pound for pound, CO2 is weaker, but there's just a lot more pounds of CO2 in the atmosphere, and a lot more pounds being produced by people. So we can compare this this is based on both the chemical properties of these gases, the way that they interact with radiation, and also the length of time they stay in the atmosphere. So you'll see on the chart, it's showing global warming potential over a 100-year time scale, which is usually the way that we talk about it, is this 100-year time scale, because some gases stay in the atmosphere a lot longer. And so they're continuing to warm the Earth a lot longer than others. So that's another difference between methane and carbon dioxide. So methane usually lasts up to about 10 years in the atmosphere. So if you emit some methane, after 10 years, that methane has undergone various sorts of chemical transformations and is not in the atmosphere anymore. So methane is very short-lived in the atmosphere. Carbon dioxide can stay in the atmosphere for hundreds of years. So carbon dioxide is going to be warming the Earth for a lot longer than methane if you emit some of both today. So when we're comparing how much warming they're causing, we have to kind of standardize the time scale for those. So methane is 28 times as powerful as CO2 over the course of 100 years. So within that 100 years, that methane's all gone. Carbon dioxide's still there. So they're warming the Earth for different lengths of time. So then another way that we can look at the effects of greenhouse gases is by examining their radiative forcing. So radiative forcing is how much change in the Earth's energy balance is caused by a particular factor. So greenhouse gases have radiative forcing, but then other things also have radiative forcing, because there are other things that change the Earth's energy balance. So by putting everything in terms of radiative forcing, we can add up all these different effects. We can add up the different things that are warming the Earth and different things that are cooling the Earth to see what the net outcome is, and to see which things are making the biggest contributions. And so therefore would be the things we'd be most interested in addressing if we want to change how the Earth's climate system is going. So this diagram shows the radiative forcing by various sorts of factors that are affecting the Earth right now. And so when the bar goes to the right from the zero there, it is a positive radiative forcing. It's something that is increasing the amount of energy held on the Earth, and therefore going to increase our temperature. If something sticks out to the left of that zero bar, it has a cooling effect. It's reducing the amount of energy on the Earth. So you can see on this diagram that CO2 has the biggest radiative forcing of any of these factors that are being examined here. So CO2, even though CO2 on a pound for pound basis is a fairly weak greenhouse gas, there's just so much of it that people are adding to the atmosphere that the added CO2, right, so these gases, this is the change in those gases caused by human activity that we're specifically looking at here. So the added CO2 in the atmosphere from human activity is having this big impact on our Earth's energy budget and therefore on our warming. Then you can see methane has kind of about half of that amount of radiative forcing. Then we've got, halocarbons are another class of gases, N2O, another greenhouse gas, right? So all of those greenhouse gases each have their atmospheric forcing, generally in a positive direction. We can see NOx has a slightly negative radiative forcing. It actually has a cooling effect on the atmosphere. Then you can see we have aerosols. So these are particles that get up in the atmosphere. And so you can see those generally have a negative radiative forcing. They have a cooling effect. That's because they're increasing the Earth's albedo. So they're making the Earth shinier. They're reflecting more light away from the Earth, right? So that's things like mineral dust, sulfates, nitrates, all of these things, when they get into the atmosphere, they lighten the color of the Earth, essentially. They make the Earth a little shinier. They reflect away more of that insolation before it can be absorbed by the Earth. And so that is going to have a negative radiative forcing and have a cooling effect because it's reducing the amount of energy entering the Earth's energy balance because it's reflecting it away back into space. Then you can also see a negative radiative forcing from changes in cloud cover. You can see a small negative radiation forcing due to albedo change from land use change. So things that people are doing that change the land cover. We talked about the urban heat island effect. So within an urban area, we're lowering the albedo and so warming things up, but that's offset on the global scale, right? That's a localized phenomenon that makes it hot in the city. But on a global scale, a lot of the things that people are doing, like clearing forests to create croplands and pastures for cattle and things, those tend to increase the albedo. Right? A cattle pasture is lighter in color, has a higher albedo than the forest that used to grow in that area. So overall, the changes to the Earth's surface albedo caused by human modifications to land use change have a small negative radiative forcing. The last bar there is changes in the actual insolation that we're getting. Right? The sun varies a little bit over time in how much energy it's putting out, and so that has this tiny little positive effect. Minuscule compared to some of these other things like the various greenhouse gases. But then we can add that all up to see the total radiative forcing. Right? Add up the positives, subtract the negatives, and you can get the total radiative forcing. How much more energy is being trapped on the Earth by these various changes to the greenhouse effect and to the Earth's albedo. And we can see that that matches up with the increases in the Earth's temperature that we've seen. And the last thing to note here is just how much human activity outstrips natural phenomena in terms of the current radiative forcing that the Earth is experiencing. So there are natural phenomena that are going to affect the Earth's energy balance and therefore affect the Earth's temperature, but the things that people are doing are so much bigger than the things that natural forces are doing at the moment. So we are having an enormous impact on the Earth's energy budget, and that is resulting in changes to the Earth's temperature. So that was a lot of information. So that will end it for this lecture, and I will see you next week.